Welcome back to another day of geometry. What we're going to do to begin with is start by practicing some of the inverse sine, cosine, and tangent practice that we did yesterday, which involves finding angle measurements within a certain triangle. And so as a reminder, if you're given a right triangle and you're trying to determine, let's say, this angle, we can use what's called inverse trig, which allows us to be able to determine angle measurement. And so within this given picture, problem number 7, what I want to make sure that you understand is that you can use this leg that's opposite that angle and the hypotenuse, and we know that opposite and hypotenuse relate to the sine ratio. So I can set up a ratio that looks like this: the sine of theta equal to 13 over 19, or the opposite over the hypotenuse. And what we said yesterday is that we can solve for theta by taking the inverse sine of both sides. And when we take the inverse sine of both sides, that essentially undoes this operation right here. Those two are opposites of one another. And then I'm going to be left with theta equal to the inverse sine of 13 over 19. And so once you have the inverse sine of 13 over 19, as a reminder, when you type that into your calculator, then what you need to press is second. Then you press the sine button that looks like the word sin. Then you type in 13 over 19, and you need to make sure that your calculator is actually in the right mode. So you got to make sure that the calculator is in the mode that says degree mode. So when I do that in my calculator, I press second sine, and I get 13 divided by 19. And as I type that in, I end up getting the angle measurement of 43.17 degrees. And that means that that angle measurement in the corner is 43.17 degrees using inverse trig. So I'm going to pause the video, allow you to go through and try and practice some of these other ones here really quick. See if we can come up with the right response. Alright, let's check and see how we did. I used inverse tangent on number 8 here and got 71.56 degrees with that ratio. On number 9, the one in green here, I used cosine and then use inverse cosine to get 38.79 degrees. And on number 10, I again used the tangent, or the inverse tangent, rather, in order to determine that. So hopefully those went well. What we're going to do in the next couple slides is just practice some application of using sine, cosine, and inverse tangent as well. Alright, as mentioned earlier, what we're going to do now is we're going to apply this stuff into context, talking about trig. And so what we're going to be talking about is climbing in Yosemite. And here on problem number 36, David and Emily are climbing El Capitan, which is a big cliff in Yosemite National Park. David is on the ground holding the rope attached to a carabiner above Emily as she climbs. When Emily stops to rest, David wonders how high she has climbed. The rope is attached to his waist about 3 feet off the ground, and he's let out about 48 feet of rope, which goes back up to the carabiner and then back down the wall to Emily's harness. The rope at David's waist makes a 55-degree angle with the ground as he is standing 20 feet away from the base of the wall. Man, there's a lot of information going on there right now, and so what we need to do is we need to draw a diagram, and I can fortunately do it right on here, and if you're on your iPad, you can do that as well if you opened this up in Notability. But since we're in the theme of triangles, there is a triangle that's being formed right now, and that triangle looks something like this. Okay, that triangle is what I've outlined, and we're told that this rope is 3 feet above the ground. So this distance here in black is 3 feet. And what he has done so far is he has let out 48 feet worth of rope. So a little bit beyond that hinge up there is 48 total feet worth of rope. And we're also told that this angle right down here is 55 degrees, and that the base of the climbing wall, or the base of the cliff, is 20 feet away from where he is currently standing. And so our first task in this problem is how long, in part A, is the rope between David's carabiner and this carabiner up on the climbing wall. And in order to determine that, I'm going to call that distance x. I don't know what it is. I'm going to use some trig functions that I know how to work with. And so in this specific diagram, what we can do is we can just draw it separately again here if you need a better visual. This is 55 degrees, this is 20, and this is x. And so I can use a trig ratio. I know that this is going to be the cosine ratio, as the cosine of theta is equal to the adjacent leg over the hypotenuse. This right here would be the adjacent leg to the 55-degree angle, and this is the hypotenuse. And as such, I can fill in those values within my triangle, noting that that is the 55-degree reference angle. So the cosine of 55 degrees is going to be equal to 20 over x. And as we've done so many times, what I'm going to do is cross multiply now and get x times the cosine of 55 degrees. And that's going to be equal to 20. And then I'm going to divide both sides by the cosine of 55 degrees, which is going to give me 20 divided by the cosine of 55 degrees. And would I do that and I type that into my calculator, 20 divided by the cosine of 55 degrees, I end up getting 34.87 feet. 34.87, feet long. And so that is the distance of the rope between David and Emily, which is this distance again here in blue. And so it says how high up the wall has Emily climbed. I'm not as concerned about that right now. What I wanted us to get in the habit of drawing was this picture and seeing how we can apply trig functions in order to help us determine some missing measurements. It all starts with drawing a picture and labeling your picture and then understanding which trig ratio we need to use to apply in order to find our missing values. We're going to try this in one more problem. It's going to be problem number 37. It says, the Bungling Brothers Circus is in town and you're a part of the crew that is setting up its enormous tent. And so it says the center pole that holds up the tent is 70 feet tall. So already what we should be doing is drawing a diagram. So there's a pole that is apparently 70 feet tall, and it's holding up this big tent, however big the tent is. And it says to keep it upright, the support cable needs to be attached to the top of the pole. So here's the tent, and there's the ground is obviously right here, and there's going to be a support cable that's going to be going up there, and that support cable forms a 60-degree angle with the ground. So we have this picture right here, and here to be a 90-degree angle. And the question is, how long is the cable? So what we're trying to determine is, what is this length right here? And so within this picture, I'm going to again call that x. If you don't see it already, we have a triangle. We have a triangle right here. And so from my 60-degree vantage point, this would be the opposite leg. This is the hypotenuse of my right triangle. So in part A, I can use the sine function, as the sine of a given angle is equal to the opposite leg divided by the hypotenuse. And so in my given situation, I can say the sine of 60 degrees is going to be equal to 70 over x. And when I solve for that, I'm going to put this over 1 and multiply both sides to get x times the sine of 60 degrees equals 70. And then when I solve, I'm going to divide both sides by the sine of 60, so I get 70 divided by the sine of 60 degrees. And typing that into my calculator, I'm going to get that x is approximately 80.83 feet. There again, 80.83 feet. So that's the length of the cable. And so then the second question says, how far from the pole should the cable be attached to the ground? So essentially, how far is this distance right here? And so that distance, which we don't know, I'm just going to call that distance z to use a different variable. We got a lot of letters going around there. There's a couple different ways that you can do that. Now that I know the length x, and I also know the 70, you could use a Pythagorean theorem. The thing that says a squared plus b squared equals c squared. Or you could use another trig ratio. If I'm trying to find this length z, I could also use the cosine of 60 degrees, because that ratio would be equal to z over 24, or 80.83. Or you could also use tangent. You could say that the tangent of 60 degrees would be equal to 70 over x. So there's multiple ways for you to be able to solve this problem if you'd like. And so it does not really matter regardless. Shoot, I should have used z there instead of x. But when you solve for z in this problem, you're going to end up getting 40.16 feet worth of length. And so the application of trig functions allows us to be able to determine many missing measurements. And so as a brief reminder, we can use trig functions within right triangles. And then we also discovered this thing yesterday talking about inverse trig, which helps us find angles, which we're going to summarize on the next slide. And to finish off this lesson, just as subtraction undoes addition and multiplication undoes division, the inverse trig functions undo trig functions of tangent, sine, and cosine. And so these are the ways that we would write them. So for example, in this problem down below, if you're trying to find the measure of this angle theta, I am given the adjacent leg and the hypotenuse, and I know that the cosine of a certain angle is the ratio of the adjacent leg to the hypotenuse. So that's how we came up with this ratio right here, 10 over 13. And in order to get theta by itself, we take the inverse cosine of both sides. And remember on your calculator, that's found by pressing second cosine. And then that'll give you that cosine with a little -1, and that's roughly 39.7 degrees. And so that's a very useful tool to help us find not only missing side lengths with normal trigonometric functions, but now we can use inverse trig functions as well to help us find missing angles. Hopefully that works well for you. If you have any questions, do not hesitate to reach out. Stay safe and stay healthy. We'll talk soon.